Right. Good morning. Good afternoon, everybody. Thank you for joining the SP Geothermal Technical Section webinar. We have our new technology webinar number 3. We are going to talk about really an interesting topic. We are really happy to see John Clegg today, an expert in drilling. I'm pretty sure the webinar is going to be really informative. I think there is a lot of evolution in well construction. Therefore, John, thank you so much for being here. The webinar is going to be 45 minutes. Then you guys can post the questions in the chat and we can review it at the end. With that being said, John, pass it on to you and thank you so much.
Thank you, Camilo, and thanks to the Geothermal Technical Section for the opportunity to talk today. Over the next 45 minutes, I'll give you a little bit of a flavor of what Hephae is doing, as it says in the title, to push the temperature limits of electronics and sensor technologies so that we can use tools that we've got used to using in oil and gas in deeper and hotter geothermal wells. I say a little bit of what we're doing simply because we're breaking new ground and we're developing tools that go in a different way. They're going to look quite different to the measurement and steering tools that you're used to seeing in oil and gas wells. And a little bit of what we're doing is under wraps until closer to the end of the year because of IP. But I'll tell you as much as I can today, and I'll certainly give you the background to the why and the timescales and stuff like that. Just as an aside, I'm actually talking to you today from Detroit, Michigan. It's the first time I've ever been to Detroit. And the reason I'm here is that TED, the TED Talks organization, has their Countdown Summit here this year. And Countdown is their kind of climate and energy based summit. And I'm hopefully you'll all be very pleased to report a lot of interest in geothermal energy to this year's TED Countdown Summit. So it's been a good place to be for the last few days. So I'll start. A lot of people ask us why the name, why are we called Hephae? And we'll get that out of the way first. We originally called ourselves Vulcan Energy Technology, and hopefully the reason fairly obvious. Sort of Vulcan was the Roman god of volcanoes and fire and the underworld and so on. And we were very pleased with our choice of name until we did a Google search and saw that there's maybe hundreds, if not thousands, of Vulcan energy companies, and then we thought we're bound to get sued by somebody if we call ourselves Vulcan. And so we had to start all over again. And we remembered that every Roman god has got a Greek equivalent, and there's a sort of equivalent to Vulcan in Roman mythology, in Greek mythology, and that is a guy called Hephaestus. And if I could get my presentation to advance, I'd be able to show you, but I can't. So this has never happened before, but I can't actually get the slide to move.
Maybe you can share again, John.
Hold on, let me try that. There we go, found it. Okay, so Hephaestus, this is his temple in Athens in Greece, and he's the Greek god of sort of fire in the underworld. And we thought Hephaestus Energy Technology was going to be a bit of a lengthy name, and so we shortened it to Hephae. We hope he doesn't mind. I really hope he doesn't mind, because he's probably not the wrong guy to get on the wrong side of. So our vision is that as an industry, we'd love to be able to drill 1 million geothermal wells by 2050. And it sounds very snappy. And why go for 1 million? And there was a bit of thought behind it. We saw the forecasts of energy consumption increasing by 2050, approximately double what it would have been in 2020. And the forecast is that at least all of that increase will be made up of by renewables. And so we thought, well, what could geothermal do? And I've been responsible for market entry in a number of countries over the years. And generally what we do when we go into a new market, or what I've done, is try and aim for about a 15% market share. It's big enough to be significant and to be profitable, and it's small enough that you don't get crushed by the competition straight away. So we looked at that, and actually, if you do the math, if you assume about 8 megawatts per well, 1 million geothermal wells gives you 16% of global energy by 2050. And it's an attainable target. I mean, if you compare it with the number of oil and gas wells that are drilled every year, 1 million geothermal wells by 2050 isn't, it's not out of the question. It's not unattainable. And so our vision is that the world will have 1 million geothermal wells producing clean electricity by the year 2050. And Hephae's mission is to be a technology enabler of the emerging unconventional geothermal industry that's going to drill those 1 million wells. By providing the technology we're working on, will allow people to drill under control, deeper and hotter wells, and create the potential for greater recovery and power generation. And we're going to develop, as you'll see later in the presentation, versions of the MWD and then the rotary steerable technologies that you're all going to be familiar with in oil and gas, and just take their temperature limits higher, take them beyond 200 Celsius, and mean that we can drill directional wells under control at higher temperature. And there is an exponential relationship between temperature and the power that you get from a geothermal well. So just a few degrees can make a lot of difference to the economics of a project. This is our company. We're based in Houston, Texas. Steve Craze, who my co-founder, is our CEO. He's normally based there. He's actually in Spain at the moment, and hopefully he's listening in, because we have opened an engineering office in Bilbao in the Basque Country. And we also have an operation in the UK, which is where I'm based. But the engineering work is going to be done broadly in Houston and in Bilbao. Houston will be primarily electronics and sensors, and Bilbao is going to be mechanical engineering, which includes a lot of very important thermal modeling, heat transfer, dynamics of heat flow, and so on. I'll talk a bit more about that later. Our core team has got about 125 years experience developing and running drilling and measurement technologies. Been working together for more than 20 years, got many patents. And diversity is very important in my mind to innovation. Not going to talk to you about it today because it would take too long, but I could show you evidence that there is a very strong correlation between diversity and innovation. And so we're very proud of the fact that we've currently got 6 nationalities and a very wide range of ages represented in our currently 8 full-time employees. And we think that's very important going forward. If any of you can read this, good luck. This is our core team, Steve and myself. Pete Harvey, who's our VP of Technology, mechanical packaging expert. He's currently in Spain with Steve, but normally based in Houston. Matthew White, VP of Systems, has got a lot of experience in high temperature electronics, based in Houston. And Christoph Bosch, who's our CFO, is based in Switzerland. So we have we're fairly geographically diverse. We're invested in by Viria, which is the climate solutions investment vehicle for Chris Anderson, who's the guy that owns TED. And that's, I think, one of the reasons why I'm in Detroit at the moment. And also partly invested in by Neighbors, who has quite a large portfolio of geothermal investments now, building a kind of geothermal and, more than that, renewable energy ecosystem headquartered in Houston. Unconventional geothermal is our primary target, and we believe unconventional geothermal is important because it's scalable globally. Conventional hydrothermal geothermal wells require that you have the right geology and particularly a source of water that could get into fissures and cracks and sort of fractures in the rock, and then be produced when you drill a well that intersects those fractures. That means that conventional geothermal is confined to places where those conditions exist, and they tend to be places associated with volcanic activity. You can think of California, Iceland, Italy, Turkey, Indonesia, Japan, New Zealand, those kinds of places. Unconventional geothermal systems, as many of you know, are much more scalable globally because they just need hot, dry rock, and the fluid is introduced as part of the production process. Inject cold fluid and get hot fluid back. There are many different flavors of them, as you can see here on this slide that we and these pictures we got from Jamie Beard with Project Innerspace. I'll give her credit for that. There are at least a dozen different ways of attacking enhanced and advanced geothermal systems at the moment. And that's very typical for technologies at this kind of stage of development. And what generally happens over the years following introduction of a new technology is that some fall by the wayside and some become stronger, and eventually you get one or two dominant modes. But it's always impossible to predict which ones those are going to be. But the interesting thing we found, and I'll show you a little bit more about this later, is that pretty much all of the EGS and AGS proposals require some form of either directional or almost always horizontal drilling to fully commercialize them. And that's why we're confident that accurate directional drilling and some kind of directional drilling system is going to be required to make this work at scale. I mentioned heat a few minutes ago, and a little bit more temperature makes a huge difference. You can see these quotes here from Baker Hughes in its geothermal sort of document produced last year. 3 wells on a 400 Celsius project produces more than 40 wells at 200 Celsius. So you could see the leverage that you get from temperature, and you can see from these other quotes as well. Unconventional geothermal is likely to require wells above 200 Celsius and maybe up to 350 or even 400. But the key is above 200 Celsius. And also, we believe that whatever system prevails, like I just said, is likely to need either directional or horizontal drilling. Horizontal drilling potentially is really useful because it allows you to drill along an isotherm, which is a line of constant temperature. There's always going to be a weak link, whether it's drilling equipment, completions equipment, production equipment, materials like cement, for example, or mud, which is going to have a temperature limit. And so there's always going to be a depth to which you can drill before things go wrong if you go any further. Once you get to that point, I think the best thing you can do is then to turn and to drill a horizontal well and keep all of your equipment at that critical temperature, because that maximizes the amount of heat you get back when you start to produce from the well. So I think laterals make a lot of sense when you start to think about unconventional geothermal. In terms of directional drilling costs, we could see how directional drilling costs have come down significantly in unconventional oil and gas. So the horizontal drilling techniques that we developed for unconventional oil and gas made huge differences to the cost effectiveness of drilling those wells. And we see that cost effectiveness and those cost improvements in drilling being directly applicable to horizontal directional drilling applied to unconventional geothermal wells. And cost is a big part of a lot of people's concern about geothermal. And I think the scaling that we saw in unconventional oil and gas and the improvements in cost that came from there should give us a lot of confidence that we can reduce the cost. So this was a view I took out of my office window when I was working in Fort Worth in 2011 or 12. And you could see they were drilling pretty close to downtown Fort Worth at the time. And the purpose of this is just to show how that combination of two technologies, horizontal drilling and fracking, completely changed the game in terms of unconventionals in the US. I mean, this was 2011, was probably about 3 years into the unconventional drilling boom, and things have got a lot better since then. We've seen how the productivity in terms of production of oil or gas from a well significantly increased over the last decade, despite reductions in the rig count. And we can also see how first production in a number of regions across the US significantly increased since the start of unconventional oil and gas drilling. So the industry's learned a lot about how to drill horizontal wells and how to drill them accurately and how to drill them effectively and productively over the last 15 years. And that is knowledge that we believe is directly applicable and transferable into unconventional geothermal. And this image is actually, it's an image that was taken from this is an image of an unconventional oil and gas sort of installation with 4 pads. We think that it's possible that unconventional geothermal could look very, very similar to this. And here's a list of people that we've looked at. We've looked on their websites. And if you look down, pretty much all of them talk about at some point using horizontal wells. With the notable exception of Sage. I think Sage is actually starting to think about using horizontal wells as well. So now everybody's talking about drilling horizontal. But it's not just direction, it's also quality. I've spent unfortunately, the whole of the COVID period doing my distinguished lecturer tour for SPE. Normally, as a distinguished lecturer, you get to travel all over the world and meet all the various sections. And mine started in September 2020 and finished in June 2021. So I did every single distinguished lecturer presentation from the spare room in my house over Zoom or Teams. But what I talked about was the importance of wellbore quality to drilling oil and gas wells. The reduction in drilling costs that you get by drilling smooth wells, the impact on completions, being able to run completions into the hole, issues with production equipment, and the image on the right here is a slightly distorted scale, but it's an image of an ESP that was run into a well, which was thought to be smooth, but turned out to be tortuous. And this particular ESP lasted, I think, 2 weeks before it failed. And when you look at the shape it was bent into, you can kind of understand why. And also impacts on production. And all of those cross over into geothermal. Because the coefficient of friction with igneous rocks tends to be higher than it is with sedimentary rocks, things like torque and drag issues because of tortuosity are going to be more difficult to overcome, both in drilling and also with completions. Tortuosity is going to be equally important if you were to run production equipment into a geothermal well. And also, just talking to somebody last week, came across the phenomenon of scaling of geothermal wells. Build-up of scale on the wellbore is easier to initiate and becomes more of a problem if you've got a rough and tortuous surface than if you have a nice smooth surface. So all of that points to wellbore quality being equally important in geothermal. And that suggests that continuous rotation is important to overcome the friction. And all of that leads us to the likelihood of using rotary steerable instead of directional motors to drill these wells, assuming they're drilled with conventional drill bits. So that leads us to Hephae's plan. And Hephae's plan is to build a high-temperature integrated rotary steerable system that combines the functions of MWD and RSS. If you look at most MWD and RSS tools that are available on the market today, there's a lot of duplication between them. They both have DNI sensors in them. They both have sort of A to D. They both have microprocessors and memory. They both have power supplies. And I think the reasons why they're separate tools are largely historic. RSS was relatively late to the game compared with MWD. And RSS, by the time RSS came along, people already had fleets of MWD tools. They didn't want to scrap them and write them off. And so you finished up with MWD and RSS being somehow connected together downhole. Now we're going into a new industry and we're developing tools for places where people haven't drilled before. And so we don't need to follow the same rules. And one of the things we realized quickly is that we can actually integrate a lot of those functions. So if we basically build an MWD tool with an RSS controller, just to control a control valve for a push the bit steering head, we can build a tool that will do everything that the current oil and gas tools do. We can build it cheaper because it's going to be shorter. And most importantly for us, we can significantly reduce the risk, because all of the risk in going above 200 Celsius is really in the sensors and the electronics. The mechanical engineering is not trivial, but we're not kind of pushing the laws of physics either. So we're fairly confident about the mechanical engineering not being a major problem, but we have to make sure the electronics and the sensors work. And one of the things we decided early on is the fewer sensors and the fewer electronic components we have, the more likely we are to succeed. And for that reason, that's a primary reason why we combine the two together. So we're currently working, we started work on development of a prototype MWD, and we are planning to have a prototype available by the end of 2024. And then we follow that with rotary steerable in 2026. We follow it with gamma in 2026, and also through 25 and 26, we start to work on increasing temperature capability. We're likely to start around 210 Celsius because that's where our head is telling us the market is going to be in 2025. People aren't going to be planning to drill hotter wells and steer them until this technology is proven. And so it's kind of baby steps. But during 25 and 26, we push our limit from 225 Celsius, and then we go on beyond that. And potentially with techniques I'll show you in a few minutes, go all the way to as far as 300 Celsius. The other thing that's worth mentioning, and I'll come back to it towards the end of the presentation, is that once we've developed the processors, the memory chips, the sensors that we can use in MWD and RSS, we're going to have a kind of box of Lego with lots of different components in it, which have been proven to work downhole at high temperature. And then that opens the door to things like intelligent completions and downhole production monitoring. And then going from that, things like software for managing production optimization and predicting production and so on. So there's quite a long runway for us in the future. But if you try and do all those things at the same time, then you're guaranteed to fail. The way to succeed is to focus. And so for the first year and a half, we're going to be entirely focused on building our MWD system, which is the one at the top of the list here. This is an image, it's out of an SPE paper. It's an image of Weatherford's HEX tool. There are a few people that claim to be able to get to 200 Celsius with MWD and LWD. Weatherford is one that I've actually seen work at 200 Celsius. And they got there not by trying to do a little bit more baking and a little bit more selection on commercial off-the-shelf components, but this was done by basically completely rethinking the materials and packaging that they used on the boards. We're going to do a similar thing. We're also going to be completely rethinking the packaging, the way that we mount the components on the boards, the way we design the boards. I can't tell you exactly what our thing is going to look like, but I can tell you it will look nothing like this. And the way we're going to do it will be kind of unrecognizable if you're looking for conventional NWD, LWD sort of boards and chassis. And the reason I say that is it's going to be very difficult to make it work if you try and make it look like an existing MWD, LWD tool. And that's one of the reasons why hiring people in a region which is not known for oil and gas and hiring people who haven't been working in oil and gas on these tools is going to help us, I think. Because, you know, my experience years ago with RSS is if you put a bunch of team together who don't know that something can't be done and they don't realize it can't be done, they actually do it because they're not hidebound by all the idea that things are impossible. So they just go ahead and make it work. And this team is going to make it work, and it's going to look very different to this. But the core principles of, you know, rethinking what you do, redesigning the boards, and using different materials that work for Weatherford are going to be principles that we use as well. There are multiple ways of transferring heat, and we occasionally get people say, well, just put all your electronics in a flask and insulate them and you'll be fine. And that would be great if electronics didn't generate its own internal heat. If you use your laptop for a while, I can hear the fan running on mine at the moment. I hope you can't. It gets hot. If you make a couple of calls on your cell phone and you put it to your ear, you can feel it. It gets very hot. And any kind of electronic device is going to be generating internal heat. So if you put it in a flask and insulate it, then you're kind of doomed because it's just going to cook itself. So the trick is actually getting heat away. And you can move heat away by convection, by conduction, by radiation, and also by advection, which is basically by fluid picking up the heat and then carrying it off, the natural movement of fluid. And you can imagine, the natural movement of drilling mud as it flows down the hole is a potential advection mechanism. And all I could say is we're looking at all of these, and we're modeling heat flow using all of these, and to a greater or lesser extent, we're going to be taking advantage of the way materials interact with all of these different thermal flow methods in order to protect our electronics. For getting to really high temperatures, 300 Celsius, and maybe even above 300 Celsius, we're going to need to use very different techniques. And there are probably people now thinking, wow, electronics at 300 Celsius, impossible, never going to work. We've had a number of conversations with JPL in Pasadena, in California. And one of the things JPL is tasked with, and a project I think was approved last year, is a Venus rover. And so a little bit like with Mars, the plan is to fly a rover to Venus and to put it on the surface and to have it relay information back. Unfortunately, Venus is not quite as hospitable as Mars. And we're not going to be getting tweets from the Venus rover for years after it's landed, telling you about what it's doing and showing you pictures of its helicopter and all the stuff that the Mars rover does. It's unlikely that the Venus rover is going to last more than about 500 hours. But it will have electronics on board, and those electronics are going to have to work up to temperatures, I believe, of 480 Celsius. And so there is technology being developed which takes us way beyond a 300 Celsius limit. And we can look to adjacent industries, and space is one, and aerospace is another one. People are looking to put sensors and processors much closer to the combustion chambers in gas turbine engines, for example, because having better sensor data will make the engines more reliable and more fuel efficient. And so there's a lot of industries outside of oil and gas that are pushing for higher temperature electronics, and to some extent, as we do our work, we can piggyback on it. We can't just buy a bunch of high temperature stuff off them and put it into a tool. Unfortunately, we've got a lot more engineering work to do ourselves, but we do have friends in other industries who we're going to be able to rely on, and who could potentially take us, as this image shows, to much higher temperatures. This is an artist's impression of what the surface of Venus is like. It doesn't look like a very hospitable place. I talked about cost earlier on, and the cost of geothermal energy is currently a concern for potential investors, but there does seem to be a general feeling that the levelized cost of electricity is going to get down to the sort of $50 to $60 per megawatt hour. That's 5 or 6 cents per kilowatt hour level over the next few years. And in fact, I think the US sort of government, as part of its sort of geothermal kind of earthshot, is looking at a reduction to $45 or 45 cents, sorry, 4.5 cents, depending on which way you look at it, by 2035. And heard yesterday from somebody who's driving the earthshot project. They've got some very ambitious targets for geothermal energy, which is great. And if you look at wind and solar and what happened to wind and solar over the last decade and a bit, you can see the impact of scale, and in particularly the LCOE of solar back in 2010 was between $226 and $270, according to Lazard. And then by 2020, it was down to between $31 and $42. And this is not unusual. You see this in pretty much every industry, and you see the impact of scale on cost. And we can expect to see, if we can use the same factory drilling techniques as we used in unconventional oil and gas, and we can drill the wells in a similar sort of way, we can expect to see the same kind of decline curves. Then I get people ask questions about, well, how much more expensive is it going to be to drill at high temperature? Because a lot of people know there's a kind of rule of thumb. For every 10 degrees Celsius you increase, the life of an electronic component reduces by about 50%. So that suggests that maybe drilling accurately at high temperatures is going to be very expensive. Well, we don't think it is. A couple of reasons. One of them is that we've got techniques we can use to mitigate against the temperature increases, and to make sure that components see temperatures they're comfortable with, rather than the maximum sort of formation temperature they might be exposed to. And the other one is that, as I said earlier, we're going to go at this stepwise, and we're not suddenly going to start drilling controlled EGS and AGS wells at 350 degrees Celsius. It's probably going to start in the low 200s and work up. And the thing that's in our favor there is time, because as we work up and get into higher and higher temperatures and potentially higher cost of drilling and higher cost equipment, the impact that you can see on the screen, the effect of scaling, the effect of experience, and the effect of time works very strongly and powerfully in the opposite direction. So if anything, there are going to be bigger forces bringing costs down as we go into higher temperature wells than there are pushing them up, simply because of the time it takes to get there. So we're very comfortable with what cost is likely to look like going into the future. So coming back to a lot of the conversations from TED this week, we think this is our time, and this is the time for industries to invest in renewables. Larry Fink, in his letter to CEOs last year, was saying that the next 1,000 unicorns aren't going to be search engines or social media companies. And spoiler alert, I don't think they're going to be AI companies either. I think, AI is another bubble that's likely to burst soon. But I think there is huge benefit in decarbonization and in producing sources of renewable energy. And for the oil and gas drilling industry, geothermal is not the only one. You've got stuff like hydrogen and CCS as possible opportunities, but geothermal is potentially a huge opportunity to create new business models and new businesses. I talked earlier about the fact that Hephae can repurpose the way that MWD and directional drilling tools were designed and optimize them. And maybe, if we could wind the clock back 30 years in oil and gas, we might design MWD and RSS in a different way. Well, we can do that because we've got the last 20 or 30 years of experience. We know what we do differently, and Hephae has the opportunity to do that and to make tools that look different. And as an industry as well, we've got the opportunity to come up with different contracting models and different business models and ways of drilling wells more efficiently, and incentivizing drilling wells more accurately and maximizing production, which is all going to contribute to the reducing the cost and improving the economics of unconventional geothermal. And it's our time, and it's also our opportunity. That, as I said, a lot of technology that can come out of oil and gas, unconventional oil and gas, and be repurposed and reworked and put into unconventional geothermal, and take geothermal to sort of scale and heights and volume that people would have thought was just impossible. Even a few years ago, even at the beginning of this decade, people might have thought we were crazy to talk about some of the vision we have for geothermal now. And my view that we're at a tipping point for geothermal has only been enhanced by some of the conversations I've heard here in the last couple of days. And as I said earlier, of course, we've got building blocks, and these are our building blocks. And those high temperature building blocks, once we've got them, it takes us beyond drilling and measurements through logging, intelligent completions, production monitoring, and optimization. So there's a very exciting future, I think, for taking the technology we've developed in oil and gas over the years and repurposing it and moving it into geothermal. And our strategy, as I said, is to become the technology enabler of the industry. So Hephae doesn't want to become a driller. It doesn't want to become an electricity retailer. Doesn't want to become a service company. We plan to be an OEM, and we plan to provide the technology that companies will need to accurately and cost-effectively drill unconventional geothermal wells. And to do that, we're going to work with operator and service company partners, and we'd love to hear from them, because I think getting the right operator and service company partners is going to help us to accelerate the sort of testing and the adoption of our tools. And so if there's anybody that's interested in working with Hephae, joining us on our journey, we'd love to hear from you. And with that, I'm going to conclude the presentation, and I'm going to throw it open to any questions.
Thank you, John, for the presentation. We welcome everybody question. Please post it in the chat and we'll read it for John. I guess, John, I'm going to start off with personal questions. When, we develop technologies for oil and gas, a big piece of the development is the field testing. Since geothermal is kind of an emerging market, obviously with a huge potential, any thoughts around the field testing for the prototypes around MWT? Any strategy that you can share with us?
Yeah, that's a really good question. Because we're enabling a new market, there's a little bit of chicken and egg involved in the, people won't drill the wells until you prove the equipment will work, and you can't prove the equipment works until people drill the wells. But there are a few strands to it. There's already people drilling EGS and AGS demonstrators, and we had brilliant news. I think it was yesterday, maybe it was Tuesday, from Utah Forge about the success of their second well, which is great news for the industry as a whole, and suggests that more of those demonstrators might be drilled. So there is potentially a lot of opportunity to test equipment at wells. They're going to be drilled, say, between 150 and 200, 185, 190 Celsius. I can't see who they are, but we get requests on a regular basis from operators and service companies wanting to drill wells above 200 C and looking for equipment to do it. So there will be opportunity to test at higher temperature. I think as soon as we can prove basic reliability, we can prove we can drill a well in a sort of more conventional temperature well. We could do a lot of laboratory work to prove that we can go above 200 Celsius, and then we can give somebody the confidence to test at higher temperatures. There are static wells that we can use where we can flow through at higher temperatures. There are already test wells that are drilled that go down significantly below 200 Celsius, for example. So we may not be able to drill on those wells, but we can certainly prove that equipment will survive and last for sort of hours, hundreds of hours, if necessary. And this one is potentially more controversial, but there may be opportunities to test this equipment in high temperature oil and gas wells. And this is potentially a big issue for the industry, and this is a big issue that was talked about. I've talked about this a few times at this tech conference, is collaboration between industries, and there's a reticence to engage with the oil and gas industry from a number of potential operators and investors and communities involved with things like geothermal energy, because there's oil and gas is the new tobacco industry now, right? There's not a lot of trust. And so there is the potential to work in high temperature oil and gas wells, improve technology, but it's not without its controversy. So that's an area all of us have to pick our way through, I think, over the coming years. But we'd be kind of foolish just to ignore it, and we'd be stupid to ignore it on kind of principle grounds. As the geothermal industry, I'm saying would be foolish to ignore the possibility of collaboration with the oil and gas industry, because there's so much overlap. and there's so much acceleration that can be done. And one thing I've told people is that it's taken exactly 100 years for the oil and gas industry to go from starting initial directional wells, and about 1930, the first onshore to offshore wells were drilled in California, and it wasn't very far offshore, right? And it's taken us 100 years to perfect the technology. And I don't think we want to wait 100 years to be able to drill directional geothermal wells. Therefore, we have to accept that we're going to import technology from oil and gas.
Perfect. Thank you, John. There is another question here. One of the targets is the hot dry rock. I guess that means really abrasive formations. From the traditional principles between push the bead and point the bead, classic RSS technologies, any deviation, variations to improve reliability of the system in such formations?
Yeah, that's a really good question. And yeah, abrasivity and friction are both going to be a problem when drilling the deeper, hotter rocks. And that's going to lead not just to issues with steering control, but with sort of torque, drag, lateral vibrations, torsional vibrations. All of the things that that tend to harm us when we're drilling oil and gas wells. Potentially a little bit worse drilling sort of geothermal wells, which is why one of the reasons why I think rotary steerable and wellbore quality are both very important. I think you can make both point the bit and push the bit techniques work in more abrasive formations. The materials you can use to protect the pads on rotary steerable tools are now, very, very high quality and very abrasion resistant. And I don't think there'll be a problem designing systems to cope with the increased abrasivity using either technique. So then it comes down to simplicity. And I said earlier, basic mechanical systems are fairly easy to make work at higher temperatures until you get things like sliding seals and rotating seals. And control systems, because they include sensors and electronics, they really need to be made as simple as possible. And it's likely that the simplest system from a control point of view and the simplest system from a mechanical engineering point of view is the kind of simple push the bit rotary steerable system. We originally saw that from Schlumberger with Power Drive back in the 90s. We now see very similar tools from other providers, sort of thinking DTEC, Halliburton with iCruise. Apologies to other people who I might not have mentioned, but there's a lot of tools that work on very similar principles, and it's likely that that will be a good principle to bring into high temperature because of the simplicity.
Thank you, Jen. I think there are two questions that might be related with each other, so I'm going to kind of put it together. The first question is about the power supply for the downhole equipment. So the first question is about what's your take on lithium batteries at that particular downhole temperatures? And the follow-up questions is around the turbines for that particular performance. So I guess the first question is, are we talking about lithium batteries or turbines? And what's the expected performance at that level, 200 degrees Celsius downhole?
So yeah, I'll take the batteries first. And yeah, lithium batteries are increasingly difficult as you get to higher temperatures, partly because of reliability and partly because as you push them towards higher temperatures, the low temperature performance becomes more of a problem. And so you potentially finish out with a tool that you can't surface test because it's too cold on the surface for the battery to operate. And also we are moving into an industry which is claiming rightly to be developing a new green, clean, renewable source of energy. And using lithium batteries isn't necessarily the most environmentally friendly way of providing power. So there's a bit of a dichotomy there as well. So it's much more likely that we'll generate our own power downhole, at least the vast majority of it. So then there are other ways of doing it, but a turbine generator is an obvious place to start. And there's no fundamental reason why a turbine generator can't work above 200 Celsius. If you have rotating seals or bearings, you just need to make sure that you do the mechanical engineering to make sure that those parts will work at the higher temperature. but that's all feasible, and we could see ways to doing that. Winding resistance might change as the temperature changes, and that's really just a question of how much copper you use. And maybe you need to make the generator a bit longer, but generally with downhole tools, with length isn't a major constraint. If we're talking about a few more inches, then that's probably not the end of the world. And then we have to handle the power that comes from the generator. But generally, things like chips for things like power management and rectification, they tend to already be built on substrates and materials that are more suitable for high temperatures, simply because those components, they tend to get hot anyway. So even though the temperature is higher, they're probably not going to be our biggest high temperature electronics and electrical system risk. So we've got a high degree of confidence that a turbine generator will work downhole. It might not be a long-term solution, but it's certainly something we're going to be looking at this year.
Perfect. Thank you, John. John, classic oil and gas, there is always a debate between downhole mud motors and rotary steerables from the balance between quality and performance. Obviously, looking in oil and gas, easy to come out with conclusions, but going forward in the geothermal, what's kind of the bet from you guys? Are you guys kind of betting on quality over performance, or performance over quality, or is a balance? What's the take on that?
We're a little bit agnostic, to be honest. I mean, we are starting off just with an MWD tool. So our first offering will be pure MWD. And if you use that, then you're either going to have to go back to sort of stabilizer placement and a black book, which is what directional drilling was kind of like when I joined the industry, or you use a downhole motor. And there are vendors producing metal-to-metal downhole motors at the moment, elastomorless motors. And there are also people producing downhole turbines with reduction gearboxes, and either of those could potentially be used to drive the bit and steer a well at a high temperature. I think they have their challenges too. I think putting solids through a metal-to-metal motor is going to be more difficult than it is putting it through elastomer motor, where the solids kind of roll through the elastomeric coating, but not insurmountable. And so there probably is a place for downhole motors to be used as steerable motors in the same way as they are in oil and gas. But ultimately, we think that tortuosity and wellbore quality is going to be more of an issue with geothermal than it is with sedimentary rocks that we drill for oil and gas exploration and production. And so that drives us to thinking that rotary steerable is ultimately going to have a bigger part to play, because it's always going to give you a smoother well. All other things being equal, the rotary steerable is always going to give you lower tortuosity and rugosity. And that will help with drilling, or help with completions. And depending on how you choose to produce the well and what the system is, it may also help with production and the maintenance and the lifetime of the well also.
Perfect. John, there is a question about the turbine. So you mentioned using turbines and magnets in the power generation side. What is the real thermal limit for those turbines? Any reference you can provide to the group?
The ultimate thermal limit is probably going to come from magnets, and I can't remember off the top of my head exactly where that limit is for the sort of high strength magnets that you need for a downhole generator. Again, as the magnets become weaker, you can just use more of them, and so it's just a little bit more length. So I don't recall off the top of my head exactly where the limit is, but it's high enough that it's not a concern for us in our looking at our development roadmap at the moment.
Perfect, John. Thank you. So there are some questions about wanting to connect with you. So we'll make the connection with you, John, after the call.
Yeah, thanks.
I think we don't have more questions. Guys, any other question? We have probably 2-3 minutes for a last question. While you guys think about the last questions, we welcome everybody for the next webinar on August 3rd, talking about waste and conversion to energy. So please check linking SP Geothermal Technical section. I got the question. So from where the geology makes sense, can we take all can we take the old oil and gas wells and extend deeper?
That's a good question. I hadn't actually thought about that. There is a lot of talk about repurposing oil and gas wells for geothermal. And there's actually a project I heard about this week, and I don't know if I can say where it is, so I won't, which is looking at drilling gas wells and with a specific aim of converting them to geothermal wells once they deplete it after a few years. So people are starting to think about oil to geothermal conversion. I'm not sure if it would be more cost effective to re-enter and re-drill an existing oil and gas well. With you know, there's always going to be sort of risk and hazard associated with that, and it might be cleaner if you want to go deeper just to drill a new well. But certainly, I think a part of the story going forward is going to be reusing oil and gas wells in some shape or form. You won't get really high production from them because generally the temperatures are going to be in the sort of 100 to 150, maybe 180 degrees Celsius range. So you're not going to be at the 200 plus that you need for sort of higher power, but at the same time your capex is going to be reduced. So you know, there's swings and roundabouts, and you know, any way of reducing the capex of these installations is potentially good. Yesterday afternoon, I visited a coal plant in southwest Detroit, which is about to be decommissioned. It's going to be demolished, I think later this year or next year. And you look at that site and you see that there's a whole host of high tension electric lines already coming in. So it's already got grid connection. That kind of site could be the perfect place to drill a geothermal installation. Unfortunately, Michigan has got about the lowest thermal gradient in the country, so Michigan's maybe not the best place to do that. But there are parts of the country where you know, repurposing other infrastructure like that could be very valuable. And certainly there was quite a bit of conversation about that I heard yesterday.
Perfect, John. I think with that, we close the session. We thank you very much, John, for the webinar. We push for geothermal. For everybody listening to the recording, follow SP GTTS, SP Connect, LinkedIn, Twitter, YouTube. Thank you very much. Thank you.
Thanks, Camilo. Enjoyed it.